Hello everyone. So in this lecture, I'm going to introduce complex potential. So this complex potential is going to help us to solve some canonical fluid problems analytically for irrotational, two-dimensional, and incompressible flows. And in such flows, we know that we have this linearity condition where we can define phi and psi based on some harmonics like sine and cosine functions. As you see, these two equations become linear, so we can define these two together, and then using this linearity we can kind of find this kind of complex potential for some of them, some flows, and then for more complex flows we can kind of use superimposition to be able to kind of add all these complex potentials together because we are now in a linear system. So we can use this linearity to actually tackle some complex flow problems. So let's get started by defining complex potential and what do I mean by this. So we define a complex potential by dividing it into real and imaginary parts. So again, in your calculus, you have heard of complex numbers where we have these kind of, where we can show different quantities in real and imaginary parts. So here, I'm going to use the same concepts to be able to combine the stream function and potential velocity. So I define this complex potential to be as Fz, which equals to the complex potential, the velocity potential plus I times the stream function. So the real part of this is going to be, of this function, is just velocity potential phi. This is the real part. And the imaginary part where I show YA, I, is going to be the stream function, okay? And Z is again a complex number where it shows the position x plus I, y. So we define x as Z as this, the complex vector. So we can, this is just to, we can simplify our notations, and this, using this complex potential is going to help us a lot to simplify our calculations. So in terms of the r and theta, I can write this as r. This equals to r cosine theta. So let's say if you have this, this is your x and y, and you want to write it in terms of, say, cylindrical coordinate system, you can do it like this. So you have, say this, I want to show it with r and theta. So this component is going to be r cosine theta, and this is going to be r sine theta. Okay, so we have r cosine theta plus I r sine theta. So I can factor r, so it's going to give me cosine theta plus I sine theta, which is what this is just based on the complex notations. This is going to be e to the power I theta. This is just a definition of this in complex notations. So it's going to be r e I theta. And so this is how we can also say, so z equals x plus iy equals to r e I theta, if I want to show it in this way. So f x plus iy equals to phi, which is the complex velocity potential, which is going to be a function of x and y, plus the imaginary part of that, which is going to be the stream function, which is also going to be a function of x and y. Okay, so this is important formula. And this is also the definition of z here. Okay, so these are important formula that this is how we define this complex potential. Okay, so there is a lemma or theorem that I'm not going to prove it here, but it states that if phi and psi are analytic, single valued, like they don't have multiple values as functions of x and y, and have continuous derivatives, then if z, this complex potential, is also analytic. And a point where fz is not analytic is called singular. So sometimes we can have some singularities in some of the problems that we are going to discuss, okay? So now I want to show what is the relation between this complex potential and velocities, okay? So this is just a definition we made based on phi and psi. So this is a definition. These are all definitions. So now I want to see what is the relation of this f with velocities, like u and v velocities, okay? So let's look at that. So complex velocity we define that complex velocity as wz, which is going to be just the f, the derivative of f with respect to z. And we want to find what is that. Okay. So let's see. So df, we know from here, is a function of x and y, right? So it's z as a function of z, which z is a function of x and y. So I can write this as partial f over partial x dx plus partial f over partial y dy. And what is partial f over partial x? F is phi plus I psi. So I can just replace that and substitute that. So it's going to be partial f over partial phi over partial x plus I partial phi over partial x times dx. And for the second term, we have similar thing. It's going to be partial phi over partial y plus I partial, this I read it. Wrote it. This should be psi partial psi over partial y dy. Okay, so this is how we have it. And now we know this, right? We know what are these. So partial phi over partial x is just a velocity u. And partial psi over partial x, if you remember, we have it here. Everything is here. Just take a look at that. So partial psi over partial x is going to be minus iv, minus v, right? And we have here I, so I need to consider that too. Oh, wait, this is not working. So it's going to be minus iv dx, and then we have partial phi over partial y, which is going to be v, and then plus I times partial psi over partial y, partial psi over partial y. What is that? It's just u. So it's going to be plus iu dy. And then I'm just going to use some tricks. So here, for this, I just multiplied by minus I squared, which is 1, right? I square, imaginary, is minus 1. So if you minus I square is going to be 1. Okay, so I just multiplied by this. So it's going to be the first, I'm going to write it minus, I just write it as I dy, and then I multiply the parentheses by minus I, so it's going to be minus iv minus I times I, which is going to be minus I squared, which is going to be 1 again, so it's plus 1, plus u. Okay, so this equals to I dy minus iv plus u. So as you see, now I can factor out u minus iv from both sides of this, these terms. So the first term is going to give me dx, and then the second term is going to give me this, which is plus I dy. Okay, so this is just some algebra. And here we know that z is x plus iy, so dx plus I dy is going to be dz. So we have df equals to u minus iv, it's going times dz. So this complex velocity that we define, which is going to be df over the derivative of df over dz, is just df over dz is going to be just u minus iv. This is the complex velocity that we define. So let me put it here. This is df over dz or wz, which is the complex velocity. Okay. So now I can set u. If we want to write it in cylindrical coordinates with r and theta, so you can set u to be ur. You can use a transformation. So use transformation. Into r theta coordinate, and then so we are going to get u is going to be the velocity, radial velocity ur times cosine theta. So this is kind of the transformation we need to do, minus u theta sine theta, and v is going to be ur sine theta plus u theta sine theta. So u theta is tangential velocity and ur is the radial velocity. So if you just replace this here, substitute it here, and then do some algebra, we can get this complex velocity for radial coordinate as well, which is going to be df over dz equals to u minus iv, which is going to be, if you do that, is going to be ur in terms of radial coordinates, ur minus iu theta e to the minus I theta. Okay, so this is also important formula. So maybe I can just just show this one. Okay, so this is because this is in both coordinates, Cartesian and also r theta coordinate. Okay, so now we are going to use this to solve some canonical flow problems and find the complex potential for some canonical flow problems. So I will do that in the next session.